Okay. Yeah. Let's begin. So we were looking at this sequence of functions, right? So we are doing this analysis on functions, trying to do it as similarly as we do analysis on numbers. So analysis on functions, or analysis of functions rather. Yeah. So before we continue, do you have any questions from last time, if you have tried anything, or questions from what we did last time?
No, we were like discussing that exchange of limits, so I'm still wondering about
Yeah, so then
exchange of
let's
limits.
continue that, right? So we were looking at this analysis of functions, and we had looked at two types of convergence. Now we are trying to motivate uniform convergence definition even more. Okay, so we are wondering this very practical question, where again, let's say to begin with, you have this sequence of functions. Okay, let's say it doesn't have to be this, but let's say that they are all from 0, 1 to r, and we had even put the condition that they are continuous. Okay? Now, the key question that we are trying to answer is when is limit n tend to infinity of yeah. So we can take anything. Let's say x tend to x naught. 1 second. Yeah. So we have this x tend to x naught, fn x. So for each function, we take the limit, and then these become numbers, and then we take the limit of that sequence of numbers. That when is this equal to you take the limit of the final limit n tends to infinity fn x. Okay, so what is the right hand? What is this? This will be a function. So here we obviously just naturally we take the pointwise limit, right? So okay, in the sense that so in the sense that you fix the x, and for each x you take you get a sequence of numbers, and you take that limit. And so this limit that you get for every x, this gives you a function of x. So this is a function of x, and you take the limit of that function, right? So both sides are well defined, but when is this equal? This is a very practical question. It's a useful in the sense all that. When does this happen? So, so do you have any answer to this? When this happens, or if this happens, then when or if this happens, then what is the consequence of this anyway? Meaning, when means what's a sufficient condition, and if would mean if this happens, then
Like
what happens?
for the LHS part, I was thinking that when you are taking that, it's like when you think of it more geometrically, the left hand side, for the left hand side.
Okay, geometrically.
Uh, yes. Mm, then you've got a sequence of functions,
Mm-hmm.
and you just draw a vertical line.
Mm-hmm.
You just draw a vertical line at x naught, and then you say that as the function as n goes to infinity, where does f of x naught go? Fn of x naught go?
Fn of x naught, yes, because it is continuous, right? So this limit is just Fn of x naught,
Right.
right? So it's exactly that, yes.
Yeah. Yeah. So that is why the vertical line, hence the vertical line.
Yeah, so the vertical line is accurate because it is continuous.
Yes. And yeah, so you just take that. So you just now, so now you just analyze the behavior of all the intersecting points on that line, and then you conclude. But on the right hand side, how do we see it geometrically?
Yeah, so on the right hand side is a bit more complicated, right? Because you first have
That's
a
what
function.
I'm not thinking about the. I am not able to figure out like what is the inner part.
Right. Yeah. So the inner part would be like for every x you have to, means for every x you have to you have to take the limit. And yeah. So how do I continue from what you're saying? Okay. So no, so I mean I think this is on the right. I mean, see, we cannot just see everything geometrically, but
No, I'm not saying, but I'm trying to see the left hand side is clear what it means, but the right hand side, the inner part is not clear. I mean,
yeah, it's a because it's a function and you don't
yeah,
know.
no, I don't see why you're saying that we fix the x on the right hand side and then we take the limit. I don't see it like that. I see that the left hand side we do that, but on the right hand side, why do we fix the x and then we take the limit?
Then what do you do? Then how do you?
See, I don't think, because the left hand side has the same meaning, right?
No, but if I mean, but
It's like on the same x naught we are taking the limit.
yes, on the left hand side you're taking the limit on x naught, but on the right hand side it is not x naught on which you're taking the limit, right? It's an arbitrary x on which you're taking the limit. Like see, this you have to return a function from here. This has to be a function, right? I mean,
Right.
this that has to be a function, right?
Yeah, I
So
got it. I got it.
yeah, that
But
is the main thing. Yeah. So let's say that the function is fx. Right. Let's just say that the function is fx. Is that all right? So let's
yeah,
see. So then if this function is fx,
then
then
if this function is continuous,
so we don't know if the
if
limit is continuous, but assuming that you can exchange the limits, assuming that, so if going to the if part, right? If this is true, if you can exchange the limits, then this is what you get so far. But then what is this? Well, this is again by definition, it is f of x naught. If that f is the limit.
right?
And so if we exchange the limit, if we
So
can,
then this becomes continuous.
yes, that's all.
And if the inner function, so then basically, if it achieves continuity, then the inner limit which we take on the right hand side, it must it resonates uniform convergence, right?
No. How does uniform convergence come?
Sorry. No. No,
No, yeah.
that's
Yeah. What we do
so
get,
if the limit is continuous, then and only then can we exchange the limits.
I don't know. What we have, what maybe that's correct, but what we have seen so far is if you can exchange the limits, then the limit is continuous.
Okay, we haven't proved the converse.
But yeah, we'll see that. Yeah. But let's note that. So that's a very interesting thing, right? That if the limits can be exchanged, then the limit is continuous. And so if the limit is not continuous, then you can say that the limits cannot be exchanged. Okay, I mean the limit meaning that function at that point only we are asking. So so far we have got this. Let me just, so let's see if we can go reverse first, then we'll try to write everything. Okay, so this implies f is continuous, obviously at x naught. This is a very interesting thing. F is continuous at x naught. Okay. Now let us see if f is continuous at x naught, can you reverse the steps? So you think, let us think. Yeah.
Okay, but if we do it like this, that let's assume that f is not continuous at x naught.
But then you will be proving the same thing, that you cannot exchange the limits. That is exactly what we have proved.
No, we have proved that. So no, what I'm saying is, what if we prove the inverse of this statement?
No, that's not the inverse of, no, that will be the contrapositive of what we have already proved, which is the same statement, right? We have
No,
proved
but
that.
if we prove that if f of x is not continuous,
Mhm.
then we cannot change the limits.
That we have already proved that.
No, we have proved that if this limit can be exchanged, then f of x is continuous, right?
So that those are the same
I'm-
statements, right?
How?
I mean,
Or
so so A implies B is the same thing as saying that not B implies not A.
yeah.
Am I correct? Yes. I mean, if A
Yes,
is true, then B is true. So if B is not true, then A should not be true, because if A is, yeah. So that we have already proved, right? And it's a very interesting thing that we have proved. Yeah, I mean, contrapositive, it's the same thing. So now we must try to, so you try to see if the converse is true. Converse,
right.
yeah. So you try to explain this to me. But uniform continuity will come into the picture. We'll see little, I think. But this will be easy. If the converse is true, it should be easy to prove.
Mm, Then let's take the right hand side. Let's go
Mhm.
from right to left.
Okay. So you are assuming F is continuous like that, right?
Yeah.
Okay.
Yeah.
So assume.
So
Mhm.
yeah,
I'm just writing it on
assume
the
f to
side.
be
Yeah.
continuous. Then limit of fn of x as n tends to infinity, we get that as f of x.
So yeah, so that does not need continuity. That is just by definition.
Yeah, but I'm just saying that.
Right.
And then the limit of this thing as x tends to x naught, as f is continuous, becomes f of x naught.
Yeah, and here we use the continuity to say this is equal to f of x naught, right?
Yeah.
Correct.
Now, on the left hand side, we are given that f1, f2, f3, so on and so forth are continuous. So limit of fn of x as x tends to x naught will be fn of x naught, obviously.
That's by continuity of the FIs. Yeah.
Given condition. Given condition. And now it's like pointwise convergence, right? On
Yeah,
the
this
left
is
hand
just
side.
by definition
Yeah,
pointwise.
this is so yeah, so we get equality.
Yeah, so the converse is true, right? So today we have an answer to when you can exchange limits. I mean, given the original functions are continuous, yeah, reasonable functions, then we have an answer to the question. So we can
Right.
erase all this. Obviously, we have just basically written it
That I
in
am
a.
being careful because to avoid. I'm just being careful in the arguments to avoid subtle mistakes or to take
Yeah,
care of
very
some.
important. Yes. And also to become comfortable, you have to be careful in the beginning. I mean, I am also trying to be careful because I am also, yeah. So this topic is a nice topic. So we should be careful. So what we have shown is that you can exchange the limits if and only if f is continuous. Okay, if and only if f is continuous. So now we should really ask, when is the limit continuous? Right, now it becomes a more, we have the motivation to ask this question, when is the limit continuous? Because that will take care of this this question of exchanging limits.
Okay.
Yeah. So now we can remove this. So that now we can remove that for the time being. Later we can try to look at that when these FIs are not continuous, then also we can ask when limit can be exchanged. But first, let's try to do a more standard this thing, and then when is f continuous? So
yeah, but we know that f is continuous. So when we obtain that like by uniform convergence, when we obtain the limit, we know that f will be continuous.
Why? Do you know that? Okay.
No, because we developed the notion of uniform uniform convergence because we wanted continuity.
Okay,
You told that.
Yes, so I mean that's what we will try to, but we have not yet proved that, right? We are far from proving that, right? Yeah. Yes, I mean it's one of the consequences of uniform continuity that the limit is continuous, but that one has to prove. We have not yet proved that. Okay. Yeah. So yes, so that's the claim. I mean, and when we try plenty of examples, we did like okay, not plenty. You should have done plenty others, but the point is that if you take any example and you see wherever you get uniform continuity, you sort of get that the final function is also continuous.
Actually, in Bartlett and Sherbert also there are not many examples like the same ones we do. Just
Yes,
only
this,
n into e raised to minus n and those things.
so it is a standard examples are mostly present. Yes, so what can you do? I mean, just search some analysis book. So I mean, T2 Andreescu has a real analysis book. You may know Kaczor's real analysis book. I mean, problem books, right? So or some other. Just see the section on uniform convergence and just try at least first 5 problems. That will be enough to get. Yeah. So do that, or just Google and see. There are many examples. Yeah. So the claim is when convergence is uniform. So basically, uniform convergence is a stricter notion of convergence, and it is so strict that the nature of the limit is similar to the nature of the sequence. Okay, and this is seen in when we see differentiability, integrability. Is the limit differentiable? Is the limit integrable? There also uniform continuity, maybe sometimes with other conditions, comes into the uniform convergence comes into the picture. And yes, okay.
Like when I was reading Bartlett and Sherbert, I realized that yes, that uniform continuity and uniform convergence have the same type of structure. For example, for the same epsilon, you always get a same delta for every x, and in the normal pointwise convergence, the delta may vary with every x.
You mean convergence or continuity?
No, sorry, not delta, n, the value of n.
The value of n will depend on x. Yeah, that n naught, yes.
On x and epsilon, but in uniform convergence, it will only depend on epsilon. It will be the same for all of the x's.
Yes, that's correct.
Yeah, but in uniform continuity, also you see that kind of structure only, right? It depends on only delta and not on x and delta, but in normal continuity, it depends on I mean, for how can I describe it?
Say.
For 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 every point on the function. So for, let's say, for example, 2 and 3, for 3 you will get a delta of 0.5, but for 2 you will get a delta of 0.2. That also happens. I mean, 0.2 you can get a delta, but in uniform continuity you will get 0.5 for all of the x's. So the same, for the same error, the same delta works for everything. So that is like a uniform thing which is going on. And for the same n, and for the same error here in uniform conversion, the same n works. And that is the major difference between uniform convergence and the normal point-wise convergence. So it's like a refined version of what we have here.
Refined version of?
Point-wise convergence.
Yeah, uniform convergence is certainly a refined version, yes. But what you're saying is, yes, there is this similarity. I mean, and all that is just the word uniform. That's how the word uniform is used in analysis.
Yeah,
that's the word uniform. It's uniform for us. So
no,
later
that's
on,
something I observed.
yes, and that's what you have to observe, these similarities among different because these names are chosen in a well understood and agreed upon way. That's right. Yeah. And you will see, you will meet, I mean, hopefully if you do more, I don't do much analysis beyond maybe analysis 3, but as you would do more, if you get into analysis, and even until analysis 3, you will meet uniform boundedness, right? You will meet something called uniform space, okay, which is a generalization of a metric space and so on, where there is some sort of a uniformity throughout, which can be used to define certain things, which can be used to lift certain notions which are available to you, like distance notion, right? We had on points, we lifted it to these things. And so this is uniform, that thing, uniform many. Yeah, there is something called equicontinuity. Okay, where there is one epsilon which works for a family of functions. For one epsilon, sorry, there is one epsilon, and then there is one delta that works not just for all points of all points on the domain of a function, but all points on the domain of all the functions. That same epsilon works. So that's a uniform sort of, that's uniform on the collection. So that's an equicontinuity. And that is needed to get some more interesting things about this. So, and there are many other kinds of uniform. I mean, but all of them are used in this similar. Yeah, so it's good to start recognizing that from the beginning. Then everything seems more natural and good. That's a so I mean, this is what you have to explain what you think, and then that's how you will get the good. So basically when is the convergence? So when convergence is uniform. Yes. So we should try to prove this. So if you have something to say, otherwise let's try to think how we can prove this.
No,
yeah, let's try to see. Yeah, so assuming that the convergence is uniform, let's try to show that it is continuous. Okay, let's think about it. You should think how we can start the proof. Then so we want to show that f is continuous, right? So we will do it point. I mean, we just show that f is continuous for fix some x naught and show that f is continuous at x naught, right? So
Yeah.
yeah. So we want to show f is continuous at x naught. So just writing the definition of continuity, f fix some epsilon. Yeah. I want to find greater than 0, so that fx minus just the definition. So f is very similar in behavior to those FIs.
For all the x minus x naught less than
Delta, sorry. Yeah.
It's continuous.
Yeah. So I will just try to draw a picture. And then here is your f. Now you have to use the FIs. Okay. Somehow.
Mm. Mm. It's like a right angle triangle. Can we use that kind of a thing?
A right angle triangle.
Because when we consider so basically when we consider the distance between two functions, we consider the supremum of them, right? Supremum
Yes.
of the distance.
Yes.
So yeah, and so basically, yeah, but that is the vertical distance, and here we are kind of concerned with. No, here also we are kind of concerned with the vertical distance only. So
Yes, this
no
is
need of
also,
right angle triangle.
yeah, this is also just the vertical distance. Right.
No, but if you just have straight line, horizontal lines,
Mm-hmm.
then how? But then, yes, but then you obviously they won't be uniformly convergent. That's the thing.
Okay. The FI is a uniformly converged to F.
Yeah.
Okay. So yeah, that is true, right? So if I just write what that means, it just means that Fnx minus Fx is less than any epsilon you want. Yeah, you can get this for all n bigger than some n naught. Yeah, let me just write epsilon 1 because for any epsilon you can. So there is basically there is a Fn which is very, very close to this F. Sort of very, very close to the F. And that is continuous. Right?
Yeah.
So that,
and then Fn of x naught, that Fn of x naught must be close to f of x naught.
yes, exactly. Yeah, because it's supremum. So for any x naught you can do. Yeah. That Fn of x naught would be close to, you said F. Okay, F of x
F
naught.
of x naught.
Yeah. Yeah,
this
we
is
can
less than
take epsilon 1. Yeah,
Yeah,
even
epsilon
any x naught. It doesn't have to be x naught, but yeah, x naught is the center
No,
here.
but we are considering the x naught point for the continuity.
Yeah.
X naught is arbitrary, but still.
Yeah.
Mm,
So this x prime is here, and just write for x prime also. Or maybe this is just more confusing, so let's not write.
mm,
Yeah.
Okay. So
Fn is continuous. You have to use that.
yeah. So yeah, that's all. Fn is continuous, then Fn of if Fn is continuous, then Fn of x minus Fn of x minus Fn of x naught. This should be less than a given epsilon 2.
Any epsilon 2, right? For all x in this delta. I mean, there is a delta.
Yeah, there is a delta. Delta naught or delta 2 maybe.
Yeah. This delta we don't really know. We have not really found, but we can use this. Now you are seeing it. So Fn, now you have to use the behavior of Fn. If Fn doesn't change too much in x minus x naught in the delta naught, then F should also not change too much, because F and Fn are almost the same at like every point. In that, that's what you formalize now.
So maybe we can say that Fn of x, so as its limit is existing at x naught, can we say that it is kind of bounded?
Bounded, yes, certainly. I mean, that is f of x naught. So f of x naught is a bounded point. It's just
But yeah, so the blue colored inequality which we have got, Fn of x minus f of x is less than, let's say we take epsilon 2 for that thing also. Okay, and we just add both of them.
Add which ones? I see three of them. So blue and
black.
Okay. Add both of them.
Or no, the blue and black. Blue and black.
Okay. So if you add them, then
you can use triangle inequality, right?
Okay. So if you use triangle inequality, then you get,
because we have proved that the sup norm preserves triangle inequality, so we can use that.
No, but here you don't need that because here you're just doing, here these are just numbers. And this is not soup norm. This is just a norm of numbers. Is that right?
Yeah.
Or yeah, maybe, yeah, but that's okay. Yeah, so this
No,
is
it's a
just,
soup norm, right? Why is it a norm of numbers? Yeah, but because you have no
okay, so
still.
you can say that, I understand. Yeah, so you can say for all x, yeah, so then in
But
that
the
case
thing
it's soup
is
norm.
that no, this is a soup norm, and the one which you are taking in the black box, that is a normal thing.
That's right. But you see, you can just
Still
say that
there are
I'm doing that for
distances.
all x. You can say that for an arbitrary x I'm doing, so it's just a normal
Yeah,
norm
but
in that sense.
still, I think, but still there are distances, right? So we can do that.
No, yes, but okay, yeah, no, but that's they are different kinds of distances in that sense. But in fact, they are not different because you are doing it for a fixed x at a time, at a point of time, right? For every arbitrary x, you are doing it, right? For any arbitrary x, this is a norm of numbers, right? And for any arbitrary x, this is a norm of numbers. And then you can apply triangle inequality. And then you can say that this holds for all x. There's no problem, right? Or otherwise, both are soup norm in some sense. In that other sense, both are soup norm, right? Because this is also x arbitrary in that range, in the delta range, delta naught range. You can use either of them. Yeah.
Okay.
So,
Yeah, obviously, yeah, you can get that right because it is the it can be thought of as the maximum x, like the maximum distance.
both
It
of
can
them
be at the
can be
end
thought
of the
of as the
band.
maximum. Yeah. So both of them can be thought of as the maximum distance. In that case, it's a soup norm, and we know that there
Yeah,
it's true.
the x which we are talking about here can be at the end of the band, delta band.
Yes, right.
Then it
Yeah,
will be a good thing.
yeah. We are basically again proving that the soup norm may we can do the triangle inequality. In a way, we are just reproving that. Yeah. Anyway, so that is okay.
So then you get when you add that, you get that. Yeah, you get this fn of x naught minus f of x is less than epsilon plus epsilon 1 plus epsilon 2. Let's just say that is some epsilon naught.
Yeah, because you can do that. Yes, right.
And now for that epsilon 1, we just replace their epsilon naught. We take a epsilon naught. And for that, we have fn of x naught minus f of x naught will be the same. And then this will be some delta naught, and this will be some delta prime. Then for a minimum delta among the delta prime and delta naught, we can have both the things satisfied.
What
So
is
again,
delta prime? What is delta prime?
So okay, wait. So basically, when we do the triangle inequality,
should I write the blue? Should I write the addition of the inequalities first? Yeah.
I'm just being careful.
Yes.
Like to check everything. Maybe it might be seem foolish right now, but I just want to be sure of each and every detail.
Yes, right. That's it.